So thank you everyone for joining us. So I'm pleased today to host Yuen-Man at the GERAD. So Yuen-Man is a postdoctoral fellow at the Australian National University. She's working with Professor Yuen-Man at the CIICADA lab. Yuen-Man is a longtime collaborator of mine, and so I'm happy to host his student over here to share his latest work. So Yuen-Man will talk about online non-stationary stochastic quasar-convex optimization. I think there's a lot of terms to define there, so yes. I'm pretty sure we'll learn quite a lot today. So Yuen, the floor is all yours. You can set up you can set up the way you want. If you want people to ask questions during the talk, at the end, and so on. This is really your time. Okay. So we'll proceed as you want. So,
sure. So I am Yuen-Man. You can call me Mandy. This is usually my friends or colleagues just call me Mandy, so feel free. And then I have been working on online optimization since my PhD. And this is a work I've done with Yuen-Man during my postdoc. This is online non-stationary stochastic quasar-convex optimization. So I'll first start with talking about what an online optimization problem is, and then I'll talk about how I apply online optimization to a class of function called quasar-convexity, and then I will talk about the regret bounds of online gradient descent when applying to quasar-convex functions. And then there's a bunch of applications that possess quasar-convexity. And so I will talk about what applications using our results. And then lastly, we'll have numerical results and then conclusion. To formulate an online non-stationary optimization problem, we will define it as a sequence of minimization problems, which in our setting is an expectation of some loss function. And here W is our decision variable, and X here is our random variable following by some distribution P. And the loss function is changing over time. And we have the time step from t = 1 to big T time of horizon. And here ft is continuously differentiable and with a non-empty minimizer set. So this problem, online optimization problem, because it's time varying, we assume that each ft should be close to each other. So we can use the information at the previous time step to make an estimate for the next time step. And that's why we want to use online optimization. Basically, the setting is like this. At each time step, we collect MIID samples. And then using this sample, we approximate the function ft to gain some information of ft. And then we update our new estimate wt + 1 using wt, and also the information at time t to make the estimates wt + 1 for the next time step without knowing ft + 1. And there are a bunch of algorithms that we can choose from. For example, online gradient descent, online Newton method, or online ABM. And then we will have the loss revealed, ft + 1 of wt + 1, and then the next time step we do the same, and then the loss revealed. And in our work, we are using online gradient descent. That is, we do an update for wt + 1 using the gradient at time t, x wt, our current time step iterate, and get a new iterate wt + 1. And performance metric we are using is dynamic regret, And basically, it is defined as the cumulative loss incurred by our estimate away from the optimal loss at each time step. Now you can see that first, we are just doing the stochastic gradient. So this, we have some tilde here. This is not the exact gradient. So this should be composed of gradient error. And then the other thing is because we use this ft to do the update, we don't know anything about ft plus 1. So if ft and ft plus 1 are close to each other, we would have the error smaller, right? So this regret should be composed of some path variations. And we want sublinear regret because when we pick the average, this will go to 0. So our goal is to have the sublinear regret bound. Okay, before I talk about quasar convexity, let me show you some existing results or some function classes that have been discussed in the online optimization literature. The most standard one is the strong convexity result. And then it is, when assuming it is smooth, we would have a regret bound in terms of the cumulative path variation. So they consider the full gradient, so they don't have any noise here, any error here. And here, for the convex one, their work established regrets bound in terms of the time of horizon multiplied by some v tilde, some cumulative path variation. The reason I wrote tilde here is that they assume they have some prior knowledge on the cumulative path variation, so they can use the knowledge to set up the step size, and that's why they have this type of regret bound. And then another one is Polyak-Loyeschwas, and this is by Kim's work, and basically they have assumed some quadratic growth property, and this is some not necessarily convex, and the regret bound is in terms of the supremum of the difference of the objective function at the current time step and next time step. And NT is the cumulative loss different from the optimal loss difference from the next time step. And then this work, in Gau's work, they assume weak pseudo-convexity, which is given like this, like something very like with star convexity, or actually very alike with quasar convexity, which we'll talk about later. And they established the regrets bound of online normalized gradient descent. So they didn't use gradient descent, they used normalized gradient descent, and they established the regrets bound. The motivation of their work is to apply it to logistic activation function, generalized linear model with logistic activation function. But as you'll see, using the notion of quasar convexity and also smoothness, we can actually improve the regrets bound when applying to logistic generalized linear model with logistic activation function. Now let's talk about quasar convexity. Let f be a differentiable function, and we start with the standard notion of convexity first. So we know that every convex function we can estimate, we can find a linear global underestimator. So every value can be lower bounded by the linear global underestimator here. And now we talk about star convexity. Let W star be a minimizer of f of W. Then we can replace this V, any V, by a fixed W star, a fixed minimizer here. So of course, we also have to replace that V with this W star here. So this is a relaxed version of convexity You see, because it is we only have this with respect to a minimizer. And you see that for star convex function, it can look like for every sub-level set, it can be like star convex instead of a convex set. So we see that here, this is the minimizer. So this is smaller than f of w, right? So this inner product must be negative, right? So for quasar-convex, we relax star convexity by multiplying the inner product with some number larger than 1. So this is a relaxed version of star convexity. Basically, we let roll between 0 and 1, and then for any w, we would have this inequality to hold. And as we'll see, this notion of quasar-convexity, we have a bunch of applications satisfy this notion. And something good about this quasar-convexity is that although this is a relaxed version of convexity, we still have similar good convergence rates, as good as convex functions. So this quasar-convexity, we have discussed, the definition is given by this. And then for the strong we also define a strong quasar-convexity. And that is basically we plus some quadratic term here, like what we have for strongly convex, but just with respect to the minimizer. Okay, we can take a look at some examples of quasar-convex function. So this is a quasar-convex function, which of course each sublet is not like convex function, and is even not a star convex function. It's just a quasar-convex function. And for this example, this is a star convex function, x squared y squared. So automatically, it is also a quasar-convex function. And this one, we see that this is an example from proposed by Yuen-Man. And the function is very complicated, but we can see that basically the sub-level set is more star convex shape instead of a convex one. So it's a relaxed version of star convexity, of convexity. So this notion was discussed in Hart's paper, first discussed in Hart's paper, and then they call it weak quasi-convexity. And they actually discuss it because they found it in the identification of a linear time invariance dynamical system. And later in the study, the structure of the quasar-convexity, and then they call it quasar-convexity because it's a natural relaxation of the star convexity. And we can also see some algorithmic consequence of quasar-convexity. In this work, they show gradient descent converges at a rate of O1 over K. K is the number of iterations. So it is as good as a convex function. And here, Kinder also proposed some accelerated methods that for quasar-convex function, it converges in O epsilon negative 1 over 2 iterations. So epsilon is the epsilon optimal point. And here, strong quasar-convex, the accelerated method converges in O epsilon negative 1 to negative 1 iterations to an epsilon optimal point. And in Wang's work, they also show this accelerated randomized algorithm that have even lower computational costs than in this method, but achieving the same complexity. And something interesting about this is that we don't know any accelerated method for Polyaklo-Yashvas function. But if a function is Polyaklo-Yashvas and at the same time Quasar-Convex, we will have strong Quasar-Convexity. So we see there, although the function can still be non-convex, there are some accelerated methods that can be applied to it. Now, for our contribution, we established regret bounds of online gradient descent for Quasar-Convex losses, strongly Quasar-Convex losses. And as a byproduct, we also developed the linear convergence of gradient descent iterates for strongly Quasar-Convex functions. So for Polyaklo-Yashvas function, we can only establish the linear convergence of the gradient descent of the function values. But this, we can establish the linear convergence for the iterates. And we apply this to a bunch of applications. For example, generalized linear models, phase retrieval problem, and tomographic reconstruction problem. And our results can improve the regret bound of Gauss work when applying to generalized linear models with logistic activation function. Go to the regret bound of Quasar-Convex losses. Assume that we have some closed convex bounded feasible sets, which is pretty standard in a standard assumption in convex online convex optimization. And then if Ft is Quasar-Convex and weakly smooth. So I didn't define what weakly smooth is, but basically it's a relaxation of smoothness. Or in other words, a relaxation of gradients, Lipschitz gradients. Then with suitable step size, we would have online projected gradient descent upper bound yields the regret upper bounded by the initialization error here, the path variation, and the cumulative gradient variance. Yeah. So it is so we see that if the cumulative path variations and the cumulative gradient error grow sublinearly, we would have the regret grow sublinearly as well. So let's compare with some existing bounds. In Zhao's work, they assume smooth and convex, and in our work, we assume weakly smooth Quasar-Convex. They use online extra gradient descent here, and we use online gradient descent. We see that the regret bound is given by upper bounded by some terms in terms of cumulative path variations, and also the cumulative supremode of the gradients between consecutive time steps. And we see that using our notion and our proof techniques, we can actually improve the regret bound here. And here ET squared is the cumulative gradient variance because we are using stochastic gradient. So there are some gradient error involved. Next, let's talk about the strongly Quasar-Convex function. We first start with the linear convergence of offline gradient descent. So assume that F is strongly Quasar-Convex and weakly smooth. We would have, with suitable step sizes, the gradient descent iterates converges linearly to an optimum like this. So W plus is our gradient descent update. We would have it's upper bounded by the contraction factor gamma with the distance from the optimum at the previous time step. And gamma here, of course, because it's a contraction factor, is between 0 and 1, and is determined by step size, weak smoothness parameter, and strong Quasar-Convexity parameter here. So this is something interesting because we previously we only have for non-convex function, we can only use polyacroyachuas and establish the linear convergence of function values instead of the equivalence. And then here is our regret bound. Assume that FT is strongly quasi-convex, weakly smooth, and Lipschitz continuous. We would have the online regrets of online gradient descent, upper bounded by, again, initialization error, cumulative path variation, and also the cumulative gradient error here. And let's compare with some existing bounds. So in Molteri's work, they assume strong convexity. And in our work, we assume strong quasi-convexity, which is something weaker than with strong convexity. And in Kim's work, they assume polyacroyachuas, which is even weaker than strong quasi-convexity. We all of our works use online gradient descent. And we see that our regret bound is as good as Molteri's work, the strong convexity one. And in Kim's work, they have other terms like here cumulative supremum between the loss function as consecutive time steps, and also NP, the cumulative difference between the optimal values as consecutive time steps. Now let's look at some applications using our results. The first application is generalized linear model. So we have some input X, and some output, which we model as some inner products of some ground truth and the input, and there's some activation function outside. And we want to find the W that best fits the input to the output. And in the online time varying setting, we assume that the ground truth varies, and we use online algorithms to solve it. The first activation function sigma that we are studying is the Leakey-Relu activation function. So we know that Relu function has been used a lot in deep neural network, and but the flat part, so the Relu is like this, but the flat part is the part that's hard to study. And this Leakey-Relu just leaks this part. So for the slope of this part is very, very small, but it makes things much easier to study. And we see that in this problem, we would have strong quasi-convexity with smoothness and also local Lipschitz continuous. Then we can apply our results and establish the regret bound in terms of the cumulative path variation and also the cumulative gradient error. And another one is the generalized linear model with logistic activation function. Again, we have some input X and output Y modeled as some inner products with some ground truth and the input X composed with some logistic activation function. And this logistic activation function is between 0 and 1. And we see that in this problem, we have quasi-convexity, we have weak smoothness, and as long as we assume the feasible set is bounded, we can apply our result, and we establish a regret bound of cumulative path variation and also cumulative gradient variance. And this is different from Gauss' work. They assume weak pseudo-convexity and Lipschitzness. But here we use a quasar-convexity and weak smoothness, and that's why we have improved the regress bound. And if we use review activation function, so this part is flat. So as I've mentioned, the analysis would be more challenging. So everything would be local. So we have locally strongly quasar-convex, weak smoothness, and local Lipschitz continuous. So we need the path variation to be sufficiently small. So we have, for every iterate, it would lie in the region that satisfies these properties. And we would have the regress bound in terms of the cumulative path variation and cumulative gradient error. Another application that I would like to talk about is phase retrieval problem. Our goal is to recover, so in a phase retrieval problem, our goal is to recover the phase from magnitude measurements. And this can be applied to X-ray crystallography, coded diffraction imaging, and optical astronomy. So in this problem, we have a set of signal ray I, AI, which we call AI here. Having these signals, we have the magnitude measurements, the quadratic magnitude measurements of ground truth with the signal of ray I here. And of course, our goal is to find a W that can best fit the magnitude measurements. And W is the phase here. And in the time-varying setting, we assume that the ground truth WT star is changing over time. So we have to do everything locally. We assume there's some region RT, and then under some condition on the signal of each ray, we would have strong quasar-convexity with Lipschitz continuous gradients and Lipschitz continuous over this region. And again, assuming we have the path variation is small, that is, the iterates would lie in the region that satisfy these properties at the next time step, then we can apply our results and establish the regress bound in terms of the cumulative path variation here. And this is the last application, tomographic reconstruction. Again, we have some ray I, signal AI here. And then we would like to, and the measurements in this form. And we would like to find a W that best fits the output here. So this problem is to recover a 2D or 3D image of the patient using the measurements of X-ray computed tomography at different angles. And this sigma here is defined by 1 minus exponential. This exponential function is to capture the occlusion of X-ray over the high density region. And this review function is to capture the sensor non-negativity of sensor measurements, and is something recently proposed in 2023. And so in the time-varying setting, we can say it's not an image, but something that is moving in the time-varying setting. So assume that each AI follows some Gaussian distribution. And then for some region, we would have strong quasar-convexity, Lipschitz continuous gradients, and also Lipschitz continuous over that region. And then we can establish the regress bound in terms of the cumulative path variation. Now let's see some numerical results. Assume that the ground truth is moving slowly and slowly and slowly. And we see there's a square root t here. So the path cumulative path variation is growing sublinearly. We consider two cases. One is idealized, so there's no noise. One is noisy, there's some noise. And then we see that for the generalized linear model, using the leaky redo or redo activation function, the regret stabilizes. So it's not growing anymore, it's all growing very, very slowly here for both cases. And for logistic activation function, both cases just grow sublinearly. And for the phase retrieval and tomographic reconstruction problem, again, we use similar trajectory. And then we see that for the phase retrieval problem, similarly, after like 100 time steps, it stabilizes because the path variation is so small. And then for the tomographic reconstruction problem, we see the red one is the noisy one, and the blue one is the idealized one. The noisy one, we see there's some linear growth at the end because the noise is constant, and the noise, noise variance is constant. And then here the idealized one is still growing sublinear. And this is a conclusion. We have formulated the online stochastic Quasar-Convex optimization problem. And then we have established the regress bounds of online gradient descent and applied it to general.
You'd buy in, think, oh, I'm going to get big money. And of course,
linear model, phase retrieval, and tomographic reconstruction. Some future directions. We have, when applying to generalized linear model, we have to assume it is noiseless. So it would be interesting to study the noisy, with noisy output, do we have similar results? Or investigate some other algorithmic consequences of Quasar-Convex functions. So this is the end. Thank you.